Welcome to the course on two-dimensional signal processing, principles and practices. We're doing the Z transform in two-dimensional way, but that is the two-dimensional signals which are to be considered in the frequency domain in terms of this Z, which is the Z transform is the generalized version of the Fourier transform, and also used in the cases of filter transfer function representation. So with that, we had learned the 2-3 examples of it, and this transform needs to be specified along with the ROC, region of convergence, whereas if region of convergent is not specified, that Z transform, which is x of z in 1D and x of z1 comma z2 in 2D, can be of different signals. So we will see them by learning the properties of this Z transform. So the case of taking the two-dimensional sequence x of n1 comma n2, whose Z transform is x, z1 and z2, and its ROC is Rx. So this Rx corresponding to this x here, and similarly for a sequence, another sequence y, whose Z transform is y, z1, z2, then whose ROC is Ry, if this is the case, and the Z transform is linear, so the property of this linearity, so we can have this superposition homogeneity together, that is a of x of n1 comma n2 plus b of y of n1 comma n2, that gives the Z transform of a x plus by, where z1 and z2 are the complex variables here. So what about the ROC, the region of convergence, which is very important in this case? It's an intersection of Rx and Ry that we had also seen in some of the examples, that we had ROC of one sequence, a part of it, and then in the sequence another part of it we had used and found the ROC of two different things, sequences, part 1 and 2, and then given the intersection of that as a common ROC, which is the ROC of the resultant sequence. So it's linear, Z transform is linear, and convolution property, which we had also learned in other transforms. So here it's applicable even. So when we convolve the two sequences, 2D sequences, that's the resultant in the frequency domain is going to be x into y. So x z1 z2 y z1 z2. So it's a product in the case of Z domain. So the ROC, what happens to the ROC? Again, the ROC is the intersection of Rx and Ry. So Rx is the ROC of x and Ry is the ROC of y. So separable sequence property of the Z transform, if the sequence is separable, and that makes the two-dimensional signal processing analysis easy. So if it is separable, then what should be the Z transform of this separable sequence? So if a sequence x of n1 comma n2 is separable by x1 n1 and x2 n2, so this x1 and x2, if you can be write in terms of two-dimensional signal into two 1D signals, then whose Z transform is also a product. It's not the convolution, as in here it is just a multiplication of x1 and x2, results in x1 of z1 and x2 of z2. So in the frequency domain, it's just a product of this individual Z transform. So easily, if a sequence x of n1 comma n2 or y of n1 comma n2 is separable, then this helps in finding the Z transform in the 1D form. So what about the ROC of this? So supposing the ROC of the first sequence is Z1, which is belong to x of z1, this one, and the second sequence x2 and 2 has the Z transform x2 is z2, and his ROC is z2 of this, that belongs to ROC of z2. So then here if the two of them would be combined in that case, like z1, and it would be belonging to z2. So the both would be used in the case of ROC for a separable sequence. So if there is a common ROC for both the cases, that then it would be the intersection. So suppose it is z1, or z1 is greater than a, or z2 is greater than b. So it depends on that z1 and z2 values, that would be a common region would be found for this ROC of a separable sequence. Now if we are taking a shift of a sequence, so if a sequence is shifted in the space domain or the time domain, in case of 1D, x of n1 minus m1 and n2 minus m2. So it is shifted in both the directions. So what would be that Z transform. So the Z transform of x of n1 comma n2 is x of z1 comma z2, and the shifted sequence will have the Z transform z1 power minus m1 and z2 power minus m2. So the shift is coming to be the multiplication in the complex variable in the case of e power j omega minus m1 and e power minus j omega m2. So this is the shift of the sequence, and what is the ROC of this shifted sequence? So this z1 and z2 should not the multiplication should not make the ROC which needs to converge. It is helping that to get the ROC to be converged. So z1 0 or infinity of this z1 and z2 should not make this transform infinite. So that is absolutely, it should be summable. So Rx with possible exceptions, z1 0 comma infinity can be used. Suppose the shift is plus, then z1 plus m1 and it is z2 plus m2. So in that case, that infinity z1 going to infinity will make this transform infinite. In this case, this z1 1 by making 0, z1 and z2 make this transform infinite. So the exceptions of z1 and z2 should be applied, depends on the shift. It is either it is a minus m1 right shift or the left shift in the 2D sequences. So these are exceptions, and other region of except the z1 0 infinity, z2 0 infinity in the z1 z2 plane, except that these points, the other places are applicable for the convergence. So it should not have the value z1 z2 should not have this value 0 and infinity. This is for the shifting sequence. So very important properties, we will see that here. And the first quadrant support sequence. So if a sequence is first quadrant, that is n1 and n2 are positive. So in that case, how do we find the initial value x of 0 comma 0, n1 0 and n2 0 for a given sequence can be found from the Z transform of it, x of z1 comma z2, where z1 tending to infinity and z2 tending to infinity. So that would result in x of 0 comma that initial value if it is a first quadrant sequence. So the same thing, finding the initial value for the third quadrant sequence, that is the support is in the third quadrant, n1 and n2 are negative. So in that case, we have this x of z1 and z2. So z1 would tending to 0 and z2 tending to 0. So you should note the difference between these two to get the initial value or the 0 comma 0 point. So which is also helpful in finding some of the transforms. So this gives the useful relation in case of Z transform. If you know the Z transform of the sequence, and then what was the initial value. So with these important properties, there are other properties also that we would not take for the discussion, which may not be useful in our applications. So we would just concentrate on these properties and the property of the ROC. So it is also important to know the property of region of convergence. So if we take the property 1, this ROC, that ROC is bounded by pole surfaces here. This we have learned already in the case of 2D. It is not poles or the excluding the pole as in the case of 1D. It is bounded by pole surfaces and is connected region with no pole surfaces inside the ROC. Like in 1D, so no pole is inside the ROC. So pole is in excluded. So similarly here in the 2D, the pole surfaces is not included in the ROC. And the second property of this ROC, that is region of convergence, is that if it is first quadrant support sequence, the sense that n1 and n2 are positive and whose Z transform is x of z1 comma z2, then for any z1 dash and z2 dash. So this can be like, we can take it like z1 equal to a and z2 equal to b. So that what we had taken in the examples in the ROC. So for any of this in the ROC, so all z1 greater than or equal to a or z2 greater than or equal to b are in the ROC. So that's what z1 greater than or equal to a and greater than or equal to b. So then these are inside the ROC. So that needs to for a first quadrant sequence. So similarly, for finite extent sequences, so the sequence which is having spreading to infinity, that's from 0 to infinity, it has a finite support. So in that case, the extent n1 and n2 are finite values. So in that case, ROC is everywhere. That means in this Z plane, except the points where it doesn't make the 0 or infinity of z1 and z2 to infinite, the x of z1 z2 completely to infinite. So it's a z1 z2 plane in which except z1 0 or infinity, z2 0 or infinity is to be excluded from that in that ROC. So this is also similar the extension of 1D, so in which you have the finite sequence in you have this z power minus 1 z power minus 2 and so on. So with substituting z equal to 0 will make the x of z infinite. So if it is having the z transform z plus z square and z cube for a finite sequence, then substituting infinite would make that z transform infinite. So the convergence needs to be found. So the ROC is all the points except these z1 0 or infinity and 0 or infinity, here z1 and z2. So that's for the finite extent sequences. And we take the stable sequence. So in case of the supposing the stable sequence, the ROC includes the unit surface like we have in the unit circle. In case of 1D, in the z plane we have the unit circle, here it is a unit surface. So the z1 and equal to 1 and z2 is 1. So ROC that is including z1 and z2. So for the stable sequence we can have like the unit circle is included here, z1 equal to z2 equal to 1 in the 2D sequences. So for example, that point z1 equal to a or z2 equal to b. So z1 dash and z2 dash, suppose this is the point, and if it is greater than or equal to 0, it will be z1 greater than or equal to 0. So this is the point greater than or equal to a of some point. If this point is not at 0, it is somewhere else here, maybe a and b supposing. So the ROC is this portion and the other portion, above portion. So the intersection of these two is the support or the ROC. This is for the first quadrant sequences. So this ROC includes this region, which is the case of the, we call this as a constraint map for the ROC of the first quadrant support sequence. We had also looked into the same thing in the case of an example, one example of the first quadrant sequence, if you recall in the previous lecture. Then for any z1 and z2 dash, what we mean here is that a and b of this magnitudes that is in the z1 and z2 plane, so which forms the line, okay, and if it is greater than, that would be in the right side and it is in the above. So the common thing is the ROC. So this is for the first quadrant support. This would shift to here for a second quadrant support, and it would shift here to the third quadrant support, and fourth quadrant it would shift here. So in this only, the ROC would shift from first quadrant, second and third and fourth and so on. So like that. So the case of, we'll take this example which we had already solved in the previous lectures. But we will use this property of Z transform and simplify that, how we can easily take the summations of the 2D summations can be simplified if it is obeying the property. So if we use the properties of Z transform. So if we take the sequence x of n1 comma n2, a power n1, a b power n2, u of n1 comma n2, how this sequence is going to be. So that we had already drawn that n1 to n2, x of n1 comma n2 is this for n1 n2 0, this gives you 1, and the u of n1 comma n2, so this is constrained to the first quadrant, and then varying n1 keeping n to 0 would result in a square a cube, and varying b n2 is 1, and this would have this b here n1 0. In this case, all this n1 0 cases b1 b2 b square b cube so on, and if we have n2 and n1 1 1, so these are the points which we have, n1 and n2 are equal. Other cases n1 is 2 and n2 is 1 and so on. So we get this sequence from the plot, just to visualize these points, and the intensity of these ones are depending on a and b values what we use. So this sequence is it, if you recall, that separable sequence. So if the sequence can be separable, yes, u of n1 comma n2 is separable, and this a power n1 b power n2 is also can be written in terms of product of 2. So when we say u of n1 comma n2, that is step sequence is separable. So u of n1, u of n2, we can write it in terms of this. And if you write this whole x of n1 comma n2 with a power n1 b n2 and separable u of n1 and u of n2, then we can combine these products like n1 terms separately and then n2 terms separately. So if we do so, this a1, this term and this term would combine into n1 u of n1 and b of power n2 into u of n2. So this is another sequence. So we can write this x of n1 comma n2 as x1 of n1 and x2 of n2. So that is, this sequence is x1 of n1 and the second sequence is x2 of n2. So this is separable sequence. So the sequence is separable, so we can write it in terms of product of two sequences, two 1D sequences. So here this is what the, so the sequence is separable, so we can easily apply the property of Z transform, take the Z transform of x1 n1 and take the Z transform of x2 n2 and then get the product of this would be the Z transform of x1 and n2. Xn, n1 here, n1 and n2 here. So separability property we can apply and get the product of these two individual ones. So what is the Z transform of the first sequence x1 n1? So here n1, because this is u of n1 and n1 is varying from 0 to infinity, for n2 can be of any value. So that is not a matter here because it does not depend on n2 here. So a power n1 u of n1, so this is going to be existing between n1 varying from 0 to infinity. So this summation can be written as a z1 minus 1 or n1 and we get the closed form solutions of 1 by 1 minus a if this is less than 1. So a z1 minus 1 is less than 1. So if this is less than 1 then z1 is greater than a. So that is the ROC for this. So from this z1 is greater than a, we can get it for this sequence, the first sequence, that is 1. And similarly for the second part x2 of n2, which is b power n2 u of n2, and taking the Z transform of this. So this sequence again can be get as 1 by b minus b in 1 by 1 minus b z2 power minus 1, and which ROC is again if b z2 minus 1 is less than 1, then only we can get this closed form 1 by 1 minus b z2 power minus 1. So the ROC is z2 greater than b. So the two ROCs and the two Z transforms. So we get the product of these two is the ROC 1 minus a z1 power minus 1 and b z2 power minus 1. So what is the ROC is z1 and z2, the common ROC, the intersection of these two. So the region of the first case results in this, the whole thing, this line, the whole thing, and the second z2 greater than b is resulting this. So the common ROC, the intersection of this two is the one which is here. So z1 and z2, this region is the ROC for this case. So this we have done with the summation. Within one summation we have done this portion of this. So now we are showing the same thing with the separability concept. So here is the ROC. So we take this similarly, the second example we had done in the previous lecture. So the x of n1 comma n2 minus a power n1 b power n2. So u of minus n1 minus 1 and n2. So is this separable or not? This sequence is separable. So if we write this sequence like if we plot it, this result in this sequence is from minus 1 to minus infinity, if you recall that n1 varying from this. n2 is taking these values, positive values, and n1 is taking the negative values only. So a minus 1, this would be minus a, and b n2 is 0 here. So this gives us a power minus 1, a power minus 2, a power minus 3 with the negative values because of that, and then we have the sequence in the second quadrant. So this sequence is separable or not? Yes, these two can be written as a product. But what about u of minus n1 minus 1 minus n2? Yes, this could also be written like the u of minus n1 to n2. So the sequence is u of minus n1 minus 1 and u of n2. So these two sequences, the sequence which is from minus 1 to infinity, this exists, and this n2 is for as the normal case of n2 greater than or equal to 0. So this would, so we can write this in terms of the product of two sequences. So the two sequences, one consisting of n1 and another depending on n2. So the product of two sequences, this is separable. So we get using the Z transform property x1 of z1 and x2 of z2. So the first sequence, and this is the summation of this sequence is limited to minus infinity to minus 1. So that's in the second quadrant region, that minus infinity to minus 1 we have seen a per n1 and z1 minus n1. So this would be resulting in the negative summation which we have change the limits as we did in the example, taking this minus n1 as m, taking the variable m equal to 1 to infinity. So we have A inverse Z1 m. So this can be like 1 by 1 minus A inverse Z1 minus 1. So and then simplifying it, we get 1 by 1 minus A Z1 power minus 1. So which is result in Z1 by Z1 minus A. So this negative sign makes this becomes the positive Z1 by Z1 minus A, but this is getting the ROC from A power minus 1 Z1 less than 1. So in that Z1 is less than A. So we get Z1 is less than A as an ROC, but the Z transform is same as the first sequence of the previous example. And similarly for the second part of the sequence, B power n2 u of n2, you can take the Z transform which is resulting in 1 by 1 minus B Z2 minus 1. So B Z2 minus 1, this should be less than 1 here. So the case is Z2 is greater than B, and so we can see the different ROCs, but the ones which the Z transform of this is similar with the previous example. So using the separability and get the product of these two Z transforms, and the ROC is the intersection of these two regions. So here Z1 is less than A, so this is the region of Z1 less than A, and Z2 greater than B is this region, complete region of this. So the intersection of the two is this region, the one which is marked with blue. So that's the ROC of this. So you can see the second quadrant sequence having the ROC in this region. So the first quadrant was having the ROC here, and the second quadrant has this here. Similarly, the third quadrant will have the ROC in this place, and fourth will have this. So this is using the separability concept. We can split the sequence into two 1D sequences and getting the Z transform of it. So now taking the third example, that A of A power n1, U of n1 n2. This U T are 2D. This is both the notations we have used in this, n1 minus n2. So what is this? This is the step sequence. This is A of n1. And what about the U of t n1 minus n2? So that's this is the sequence here, and this is known. This has carrying the values 1 1 everywhere. That if we multiply this with ut of n1 minus n2, ut of n1 minus n2 is the diagonal one which is existing above this region, and including the negative ones. So this ut of n1 minus n2, if you recall that it's not the case, if you multiply this, diagonal ones is not separable. So if we multiply these two sequences, so we get only this portion of that, and also we have in the sequence A power n1. So it depends on that, this intensity values would change, or these points would change 1 here because n1 is 0, and n1 1 2 3 4 and so on, a square a cube, a square a cube, this continued here as well. That means here in the sense it is the diagonal, and here it's completely, this is up to this. So it would grow for infinity. So this is not the case of U of n1 n2 n1 and n2, because if you see this U of n1 n2 can be separable. So the step sequence is separable, but the diagonal step here is not separable. So we cannot write this because this is having the slope of n equal to n2, and we cannot write this for a to be separable. We need to write this in terms of x1 and x2, the product. So it is depending on n1 and n2. So we will not be able to separate this sequence, and so we should not use the separability concept of taking the two sequences, or it's not applicable basically. So we will not be able to find the Z transform using the separability concept of separating into two. So because of this diagonal one which is not separable. So in the previous examples, this the portion of each in the sequence are separable. So we could write it in terms of the product of two sequences. So this is not separable. So the way in which we solved this problem in the previous lectures, that needs to be followed for summation. So because n2 is depending on n1 here. So we take the next example, in which the example 4, that is find the ROC of this. So, so far we had done the Z transforms with the separability concept as well. So, some complex cases of sequences like x of n1 comma n2 is n1 plus n2 factorial and n1 factorial and n2 factorial. So, this particular sequence which we have already a power n1 b power n2 u of n1 comma n2, and there is a n1 n2 dependence here as well. Okay, so the amplitude of this sequence is n1 plus n2 factorial, n1 factorial and n2 factorial. So, if we consider this and plot the sequence. So, this sequence we had seen u of n1 comma n2, and it would have the values a, b depends on n1 and n2. We have plotted it and we have solved it, and we have also found the Z transform through the separability concept. Now, adding this or multiplying this signal with the factor sum. So, thus that would result in this 1a square. So, if we suppose we take this case n1 equal to 2 and n2 equal to 2. So, this is 2 factorial and 2 factorial, and 2 plus 2 4 factorial, 4 factorial by 2 factorial, which results in 6 here. So, that is 6 into a square and b square. So, similarly for the other cases as well, it depends on n1, n2 and so on. So, this is the sequence. Now, this sequence extends this way. This would extend here and here as well. So, as n1 is varying and n2 is varying. So, the u of n1 comma n2 restrict this sequence to be in the first quadrant. That's it. So, now finding the Z transform of it. So, x of n1 comma n2. Now, write this one. So, this is the sequence n power n1 n2 u of n1 comma n2. So, now the restriction here is this between, it is not from minus infinity n1 and n2, whereas this one is from 0 to infinity and 0 to, because of the sequence is restricted here. Now, getting this the factorial a and z1, combining these two cases, a of a z1 power minus 1, b z2 power minus 1 here, and the factor comes here. So, we try to simplify this. What is the summation for this case? So, let us take n1 plus n2 as m. Okay, so that is the case. If we take m, and what is this is n factorial, and what is n2? n2 equal to m minus n1. So, that is what we have put here, m minus n1. So, to get the closed form solution, this n, and n1 is varying from 0 to infinity, and n2 is varying from 0 to infinity, which is n2 equal to m minus n1. So, where in terms of, if we write it m equal to n1 to infinity. So, if we change applying the limits here, we get m is varying from n1 to infinity. So, this would the m equal to 0 to infinity, just interchanging the summation n1 0 to infinity here. So, we get how do we get the closed form solution? So, supposing we have x and y whole power m. So, in which this n1 varying from 0 to infinity, m factorial and n1 factorial, m minus n1 factorial, x power n1, y m minus n1. So, we have this summation is the resultant of x plus y for m. So, for the m values which are greater than or equal to 0. So, m those other values of m is not valid. So, using this summation, so resultant, we can write this previous summation here. So, this one to x plus y. So, x plus y, which is nothing but a z1 power minus 1 in our case, and b z2 power minus 1 whole power m. So, the whole right hand side is simplified to a z1 power minus 1, b z1 power z2 power minus 1 of m, where m is varying from 0 to infinity. So, this case now, if it is, this is a Z transform we are going to take. So, if this is going to be less than 1, the whole thing which is within the bracket, then we can write this as 1 by 1 minus a z1 minus z1 power minus 1, b z2 power minus 1, 1 by 1 minus a power m. So, the ROC is obtained from a z1 power minus 1, b z2 power minus 1 less than 1. So, this case, getting the ROC for it is, we can simplify it as well. The case is, we take this a, b, and from this equation we can simplify this to z2 equal to b z1 by z1 minus a for any value of z1. So, this curve z2 greater than or equal to this is this curve which is represented here. Okay. So, the ROC is this portion, it is not the straight line, and it is not the case of a dotted are the portion of it. So this resulted Z2 is resulting a curve which is here, Z2 equal to B Z1 in by Z1 minus A. Okay. So this curve represent the equation of the ROC from this. So if you just write it as A by Z1 plus B by Z2 less than 1 and simplify it, we can get this. This one is Z2 equal to B Z1 by Z1 minus A. So these are the fold surfaces, like, so just to show that B Z1 by A minus Z1, we compute it Z2 as B Z1 by Z1 plus A. So these two are the curves shown here are the pole surfaces, and this which is resulting here, which is of no use in this case anyway. So the ROC is defined from Z2 greater than or equal to this. So this is the portion which is the ROC, and just to show the pole surfaces that is not part of the ROC here. So this is the ROC in this case. So we have taken the few examples of two-dimensional Z transform, in which we have shown the separability concept, how the separability concept can be used for two-dimensional sequences which are separable, and so the 1D Z transform can be applied to it, and taking the product of these two sequences of 1D Z transform will also be the product of two 1D Z transforms. So two sequences of 1D in time domain or the space here, and the Z transform also is the product of these two individual sequences Z transforms. How this makes this easy, and if this sequence is not separable, then the separability concept cannot be applied. So we need to go for the summation, what we have done this in the previous lectures. And we have also shown the Z transform in which, if it is diagonal sequences which are having the step sequence which is with the diagonal ones, so are not separable. The example which we had taken last one, so the pole surfaces have been shown, and we have got this ROC which is Z1 and Z2, the Z2 greater than a curve is the common ROC which is to be found in the case of the example which we had taken. So these little complex example we had taken to show that Z2D Z transform, and with the few more Z transform examples, and then we will also do the case of inverse Z transform in the next lecture. Thank you.